Imagine standing before the door of a cosmic vault, a place where the laws of physics cease to make sense. Have you ever wondered what lies inside a black hole? Traditional science tells us that anything crossing the event horizon is doomed to eternal oblivion, crushed into a point of infinite density. But is that really all there is? Are black holes merely insatiable devourers? Or do they conceal secrets that could change everything we know about the universe? What if I told you that some theories suggest black holes might be portals to other universes, or that all the information of what enters them could somehow be stored at the edge, like a hologram? It may sound like science fiction, but some of the brightest minds in science have proposed hypotheses that challenge our understanding of space-time. The truth is, no one knows exactly what happens inside them, but we have clues, and each new discovery about these invisible giants brings us one step closer to unlocking the deepest mysteries of the universe. So, if you're ready to embark on an epic journey to explore the enigmas of black holes, buckle up. What you're about to discover might challenge everything you thought you knew about reality. Underscore. Black holes defined by 3 numbers. Imagine trying to describe a star. You'd need to list its size, chemical composition, temperature, luminosity, and an endless number of other variables. But black holes? They follow much simpler rules. Every black hole can be fully described by just 3 numbers: mass, electric charge, and angular momentum. That's it. This simplicity is almost poetic, considering we're dealing with one of the most extreme phenomena in the universe. Now, think about this. If we only knew a person's height, weight, and hair color, could we describe them completely? Obviously not. But black holes work differently. Everything that happens beyond the event horizon seems irrelevant to the outside world. They are like cosmic vaults, hiding inaccessible secrets, and science is still trying to understand what really happens inside them. This is where the mystery starts to get intriguing. This concept defies our intuition. If we take 2 black holes with the same mass, charge, and spin, it doesn't matter what has fallen into them: stars, planets, or even an entire library of information. In the end, they would be indistinguishable. This idea became known as the no-hair theorem, because, much like a bald head, black holes have no distinguishing features beyond these 3 variables. And here arises the big question: what happens to all the information that falls into a black hole? Does it vanish forever? Or is there a way to retrieve it? This dilemma shakes the very foundations of science and theoretical physics. Stephen Hawking dedicated much of his life to this problem, and his answer sparked one of the most heated debates in astrophysics. But before diving into that controversy, we need to understand how these cosmic giants are born and evolve. If you think a black hole appears out of nowhere, it's time to explore the fascinating processes that lead to their formation. Formation and evolution. Black holes don't just appear out of nowhere. They are the ultimate result of the evolution of certain stars. When a massive star burns through all its nuclear fuel, gravity wins over any resistance and collapses the star's structure. What remains? A black hole. But this isn't the only way they form. Smaller black holes can emerge from the merger of even tinier ones, or from the collapse of massive gas clouds in the universe's early days. Now, imagine a lake absorbing rainwater. At first, small droplets join the surface, but over time, the lake grows, engulfing everything around it. Black holes work similarly. As they accumulate matter, they expand. This growth can accelerate when they consume nearby stars or merge with other black holes, forming even more colossal versions. But here's the most intriguing part. Everything a black hole consumes seems to disappear forever. The information about the matter it devoured isn't recorded anywhere, or at least, that's what it appears to be. This raises one of the greatest questions in science. Is the information that falls into a black hole destroyed, or is there a way to recover it? The idea that information could be lost forever contradicts the laws of quantum physics. After all, everything in the universe must, in some way, be reversible. This means that a black hole's entire history might be written somewhere, even if we can't read it. Some scientists believe that this information is encoded on the black hole's surface, while others argue that it may be lost forever. But what if everything that has ever fallen into a black hole still exists in some form, just completely inaccessible to us? To understand this mystery better, we need to explore the concept of the event horizon, the true point of no return for these cosmic monsters. The event horizon and the point of no return. Imagine sailing a boat on a calm river when, suddenly, you approach a massive waterfall. There's a point where if you cross it, there's no turning back. The current is too strong and nothing can stop your fall. This is the same principle as a black hole's event horizon. It marks the ultimate boundary. Anything that crosses it is doomed to never escape, not even light. This boundary isn't a physical wall, but rather a region of space where gravitational force becomes so intense that no information can escape. The size of a black hole's event horizon is determined by its Schwarzschild radius, which depends only on its mass. To put this into perspective, if Earth were compressed into a black hole, its event horizon would be only 9 millimeters in diameter, smaller than a coin. Now, here's a curious detail. If you were falling into a black hole, you wouldn't feel anything as you crossed the event horizon. But to an external observer, you would appear frozen in time, as the light reflecting off your body would grow weaker and more distorted until you completely vanished. It's as if you were trapped in the limbo of your own existence, never really crossing the final threshold, at least from the perspective of an outsider. But here comes the mystery. What happens after something crosses this boundary? Relativity tells us that everything must be crushed into a point of infinite density, known as the singularity. But this creates a massive problem for science, because our laws of physics simply stop working in that scenario. Something is missing, some crucial piece of the puzzle that we have yet to understand. And what if all the information that has ever fallen into a black hole still exists somewhere, hidden in an unexpected place? Stephen Hawking spent decades on this question, and his discoveries completely shook our understanding of how these cosmic giants work. The Forgotten Past, Information Paradox. Now, stop and think. Everything you've ever experienced, every word you've ever spoken, every moment of your existence leaves a mark on the universe. But what if there was a place where all that information simply disappeared? This is exactly what Stephen Hawking realized when studying black holes, and his discovery changed science forever. If everything that enters a black hole never comes out, it means the information about what fell inside could be erased from the universe. But that doesn't make sense. The laws of physics state that information can never be destroyed. This contradiction became known as the black hole information paradox. Imagine you tear a piece of paper and burn it into ashes. At first, it seems like the information is gone, but in reality, every particle of smoke and ash contains traces of the original paper. With the right calculations, it would theoretically be possible to reconstruct it. But when something enters a black hole, well, that's a different story. Nothing comes out. The information vanishes. And this defies everything we know about quantum mechanics. Hawking attempted to solve this problem with a revolutionary concept. Black holes might not be as black as we once thought. He proposed that due to quantum fluctuations in space near the event horizon, black holes actually emit a faint, steady radiation. This radiation became known as Hawking radiation, and here's the scary part. It means that black holes over time lose mass and eventually evaporate. But this raises another question. Where does the information of everything swallowed by the black hole go when it disappears? This is one of the greatest unsolved mysteries in the universe. Could it somehow return to space? Or does it simply fade out of existence? Some physicists suggest that the information might be encoded in Hawking radiation itself, but no one has been able to prove it yet. And if a black hole could truly vanish, all that would remain is one final burst of energy. But before diving into that, let's take a closer look at the bizarre phenomenon known as Hawking radiation. Hawking radiation and black hole evaporation. You've probably heard the saying that nothing escapes a black hole, right? Well, Stephen Hawking proved that this isn't entirely true. He discovered that, due to quantum effects, black holes emit an extremely weak radiation. This process, now known as Hawking radiation, causes the black hole to lose energy over time. And what happens when it loses energy? It shrinks. In other words, if a black hole stops feeding, it can quite literally evaporate. But how does this work? The vacuum of the universe isn't really empty. It's filled with particles and antiparticles that constantly appear and disappear. Near a black hole's event horizon, these particles can form in a special way. One falls into the black hole while the other escapes into space. The result? The black hole loses a tiny fraction of its energy each time this happens. Now, before you imagine black holes evaporating before your eyes, it's important to remember that this process is incredibly slow. For a black hole the size of the sun, it would take trillions of times the universe's current age to completely vanish. However, smaller black holes, like those that might have formed right after the Big Bang, could have already evaporated, releasing their final burst of energy in colossal explosions. If this theory is correct, it could help solve part of the lost information mystery. Maybe the remnants of everything that fell into a black hole are released in its final phase, when it disappears. But what does this radiation actually carry? Is it just ordinary particles? Or is there a hidden code that could tell us what was once inside the black hole? This question leads us to an even stranger concept. What if all the information in a black hole isn't lost inside, but is actually imprinted on its surface, like a hologram? This seemingly crazy idea might completely change how we see the universe. Quantum mechanics and the holographic principle. Now, get ready for an idea that sounds straight out of a sci-fi movie, but it could be one of the most profound discoveries in modern science. What if everything that happens inside a black hole, every particle, every atom, every trace of information, is actually encoded on its surface, like a hologram? This is the foundation of the holographic principle, a theory that suggests our three-dimensional reality might be nothing more than a projection of information stored on a two-dimensional surface. Sounds absurd? Maybe, but the math suggests this hypothesis makes a lot of sense. Just like a hologram on your credit card can store three-dimensional information in a thin plastic layer, black holes might store everything that happens inside them on their outer boundary, the event horizon. This would explain what happens to information when something falls into a black hole. It doesn't disappear, it just becomes trapped on the surface, inaccessible to us. But this idea isn't limited to black holes. Some scientists believe the same principle might apply to the entire universe. In other words, what we perceive as a three-dimensional reality might actually be a projection of information stored on a vast cosmic two-dimensional layer. It's as if the entire universe were one giant hologram, and we're living inside it without realizing it. If this is true, it could change everything we know about the relationship between gravity and quantum mechanics. After all, the greatest challenge in modern science is finding a theory that unifies these two fundamental forces. The holographic principle might be the missing bridge between the subatomic world and massive cosmic phenomena. But black holes still hold even more secrets. After all, if they emit radiation and store information, does that mean they also have temperature? The answer might surprise you. Black holes have temperature. Black holes are often described as endless cosmic devourers, swallowing everything around them without giving anything back. But here's a twist that changes everything. They actually have temperature. This means that, contrary to popular belief, black holes are not completely cold and inert. In fact, they follow the same thermodynamic laws that govern everything in the universe, including heat, entropy, and even a kind of lifespan. Stephen Hawking realized that if a black hole emits radiation, then it must have a temperature. But here's the interesting part. The bigger the black hole, the colder it is. A black hole with the mass of the sun would have an absurdly low temperature, less than a billionth of a degree above absolute zero. Meanwhile, smaller black holes can reach incredibly high temperatures and evaporate much more quickly. This discovery leads us to another fascinating concept: entropy. Simply put, entropy is a measure of disorder in a system. The greater the entropy, the more chaotic it is. For black holes, the more matter they consume, the higher their entropy. This suggests that black holes don't just store information. They also have a limited storage capacity, regulated by their temperature and entropy. Now, imagine you have a super powerful computer and decide to fill its hard drive with billions of files. Eventually, it will run out of space and be unable to store anything else. Black holes seem to follow a similar logic, and this could give us clues about how information is structured in the universe. After all, if a black hole has temperature, that means it can lose heat. And losing heat means losing mass, eventually leading to its evaporation. But if we can't see a black hole directly, how can we study its properties? The answer lies in the gravitational effects they exert on everything around them. Now, let's explore how scientists manage to detect these invisible giants scattered throughout space. Detection of black holes. If black holes are invisible by definition, since not even light can escape them, how do scientists manage to find them? The answer lies in the universe's side effects. Just like you can't see the wind but can observe its impact on swaying trees, black holes also leave visible traces that reveal their presence. And believe me, these traces are nothing short of spectacular. One of the most effective methods for detecting a black hole is by observing its gravitational influence on nearby objects. If a star is orbiting something invisible at an absurd speed, that's a strong indication that a black hole is nearby. This is exactly how the supermassive black hole at the center of the Milky Way was identified, by studying the orbits of the stars surrounding it. Another way to detect black holes is through the radiation emitted by matter falling into them. When gas and cosmic dust spiral into a black hole, they form an accretion disk spinning at incredible speeds. This process generates an enormous amount of energy and emits extremely bright X-rays. So, even though the black hole itself remains invisible, its cosmic meal becomes impossible to ignore. And then we have gravitational waves. In 2015, the LIGO Observatory detected, for the first time in history, ripples in space-time caused by the collision of two black holes. This event confirmed predictions Einstein made a century earlier and opened a brand new way for us to study these cosmic monsters without ever needing to see them directly. It was as if we had gained a new sense to perceive the universe. But despite all this progress, we are still only scratching the surface of what we can discover. The truth is, black holes may be the key to something even greater, the unification of the fundamental forces of physics. And if we solve this puzzle, we could be on the brink of a revolution in our understanding of the universe. The future of black hole research. Black holes are more than just exotic objects in the universe. They may hold the key to answering some of the deepest questions in science. After all, modern physics has a major problem. General relativity, which describes gravity and large celestial bodies, doesn't quite fit with quantum mechanics, which governs the subatomic world. But black holes exist precisely at the crossroads of these two fields, making them the perfect laboratory for a potential theory of everything. One of the biggest hopes for the future of research is to better understand what happens inside the event horizon. New technologies, such as more advanced space telescopes and highly sensitive gravitational wave detectors, could help us map the influence of black holes on space-time with greater precision. This might lead us to answers about the nature of singularities and whether something exists beyond them. Another promising advancement lies in artificial intelligence and machine learning. Scientists are already using these tools to analyze vast amounts of astronomical data, identifying patterns that the human eye would never notice. This could allow us to find smaller black holes, predict their mergers more accurately, and even simulate the conditions inside a black hole with greater detail. And of course, there's always the possibility of completely unexpected discoveries. The holographic principle itself raises an even deeper question. Could all of reality be explained through information encoded in ways we don't yet comprehend? If this is true, then black holes might only be the tip of the iceberg of knowledge that could revolutionize our understanding of the universe. But one thing is certain: the more we study black holes, the more questions arise. And that brings us to the final question: what really lies inside a black hole? The answer might be far more surprising than anyone ever imagined. Black holes challenge everything we know about the universe. They consume matter, distort space-time, and hide secrets that could completely change our understanding of reality. But what if I told you that these cosmic giants might be directly connected to the greatest mystery of all, the Big Bang? Think about it: a black hole collapses everything into a single point of infinite density. Now, compare that to the beginning of the universe, an infinitely dense point from which everything emerged. Coincidence? Or is there a hidden connection between black holes and the origin of everything? Some scientists believe there is a deep link, one that could reveal what existed before the Big Bang. If this idea sparked your curiosity, then you need to watch my other video, What Was the Big Bang? In it, we explore the most fascinating theories about the birth of the cosmos and how everything we know might have come from nothing, or perhaps from something even stranger than we can imagine. The answer to black holes might lie in the origin of the universe, and the answer to the Big Bang might be hidden inside black holes. So, click on the next video and come find out what really happened when everything began.